Beneath the French countryside, sealed off from the world by 100 meters of solid rock, a machine is doing something no civilization before ours has ever managed. It is breaking matter open at the most fundamental level physics will allow. The Large Hadron Collider drives twin beams of protons around a 27-kilometre ring at 99.9% of the speed of light. The collisions that follow reach temperatures approaching 10 trillion degrees, and the data coming back from those collisions is quietly dismantling a framework that physicists have trusted for half a century. Tonight we are going inside that machine. We will cover the particles that refuse to behave, the hidden layer of reality too small for any instrument alive to reach, the invisible majority of the universe that physics cannot explain, and a calculation about the ground state of the universe itself that some physicists genuinely struggle to say out loud. This one goes deep. If this kind of content does something to you, subscribe now, because what we are about to cover changes how you see everything. Here is everything you need to know. Somewhere beneath the rolling farmland that straddles the border of France and Switzerland, sealed away from every noise and vibration on the surface, sits the most powerful instrument the human species has ever assembled. You would never know it was there. A few low industrial buildings scattered across the landscape, some ventilation ducts rising out of the grass at irregular intervals, power lines cutting across the horizon toward the facility. Nothing about the surface gives the machine away. There are no signs, no dramatic architecture, no indication whatsoever that something world-altering is happening below your feet. What the machine is doing underground is this. It is recreating conditions that have not existed since the universe was less than a heartbeat old. Scientists are driving protons together with enough force that the collision point briefly becomes one of the hottest places in the known cosmos. Not the hottest place near Earth, not the hottest place in the solar system. One of the hottest places anywhere in the observable universe, recreated deliberately under controlled conditions, inside a tunnel buried beneath farmland in a landlocked region of Western Europe. That collision point, a region smaller than a single atomic nucleus, touches temperatures that existed only in the first fraction of a second after everything began, before stars, before galaxies, before atoms themselves had any right to exist. The machine is called the Large Hadron Collider. Its tunnel runs in a circle measuring just over 27 kilometers in circumference. If you drove that loop on an open road at highway speed, it would take you roughly 20 minutes. That is not a particularly large circle by any ordinary measure. But inside that tunnel, sealed inside pipes thinner than a human arm, proton beams complete that same circuit 11,000 times every single second. Not 11 times, not 1,100 times. 11,000 complete circuits every second. If you blink, the protons have completed roughly 15,000 laps before your eyelid opens again. At any given moment, the two beams together contain hundreds of billions of protons, and every one of them is racing in opposite directions around the ring at a speed so close to the speed of light that the difference between their velocity and the absolute speed limit of the universe is less than 4 meters per second. The magnets that hold those beams on course are cooled to minus 271 degrees Celsius. That is colder than the surface of Pluto, which already sits so far from the Sun that sunlight there is roughly 1,600 times dimmer than it is on Earth. It is colder than the background temperature of deep space, which itself sits just a few degrees above absolute zero. The engineers who built this machine had to construct the largest ultra-cold object on Earth just to keep the protons aimed correctly around the ring. Nothing in the natural environment near our planet is this cold. This coldness had to be engineered from scratch and maintained continuously, year after year, by cryogenic systems running without pause. The project took decades of design and construction before the first beam circulated. Scientists from more than 100 countries contributed components, calculations, and expertise to it. When it first powered up in September 2008, there were people standing outside the facility carrying signs warning that the collisions would generate a microscopic black hole capable of swallowing the Earth from the inside. Tabloid newspapers ran headlines about the end of the world. Philosophers wrote essays about scientific hubris. A handful of legal challenges were filed in multiple jurisdictions, attempting to halt the experiment on safety grounds. The physicists checked the mathematics carefully, reviewed every calculation from multiple independent angles, and concluded with high confidence that the scenario being described was physically impossible. They switched it on regardless. The Earth survived. But something else began that day. Something quieter and, in certain ways, more genuinely unsettling than any black hole. The machine started producing numbers that did not match the predictions, not dramatic failures, not readings that were completely off the scale, small deviations, fractions that looked like rounding errors at first glance, except that they kept reappearing in independent experiments run by separate teams using separate instruments at separate points around the ring. The rulebook that had governed particle physics for 50 years began showing signs of strain, not in one place, in several places simultaneously, and the more carefully scientists looked, the more signs they found. The machine did not end the world. It may instead be showing us that the world is stranger and deeper than the best physics we have been able to write down. There are roughly 2,700 scientists working on the collider right now, scattered across dozens of countries and hundreds of institutions. A substantial number of them are chasing a version of the same thing. Evidence of a layer of physical reality that sits below anything a human instrument has ever reached. A layer where the current rules may not just bend but collapse entirely. Where forces that have no names in any textbook and particles that no detector has ever caught might be operating in ways that determine everything about the universe above them. The mass of every particle, the strength of every force, the reason anything exists at all rather than nothing. The search for that layer is what this is about. The machine buried under Europe is the most precise instrument ever constructed by the human species. It draws enough electricity to power a medium-sized city around the clock. Its largest detectors outweigh the Eiffel Tower. And after decades of operation, accumulating data one collision at a time, it is closing in on something that defies every framework physicists have trusted since the middle of the 20th century. What exactly that something is, no one fully agrees on yet. The theoretical models being proposed to explain the anomalies are diverse and sometimes incompatible with each other. But the data itself keeps pointing in a consistent direction. And the researchers who spend their careers staring at that data, the people who know it most intimately, are starting to look genuinely uneasy, not worried, not panicking, something more specific than that. The expression of someone who suspects the thing they have been chasing for decades might actually be there and is not entirely sure they are ready for what finding it means. For 50 years, a single theoretical document has governed particle physics. Scientists call it the Standard Model. It is a mathematical framework, a precise and interlocking set of equations that describes every particle ever detected in any laboratory anywhere in the world, and accounts for 3 of the 4 fundamental forces that shape the universe at every scale smaller than a galaxy. It covers the electromagnetic force, the force that underlies chemistry, generates light, drives electrical current through every wire ever manufactured, and holds electrons in orbit around atomic nuclei. It covers the strong nuclear force, the force that locks quarks together inside protons and neutrons with an intensity so extreme that it makes the electromagnetic force look trivial by comparison. And it covers the weak nuclear force, the force responsible for certain types of radioactive decay, and for the nuclear reactions that powered the early universe through its first few minutes of existence. 3 forces, dozens of particles, thousands of independent experimental confirmations. It is the most thoroughly tested scientific theory ever produced by the human mind. experiment after experiment across decades, and across every particle accelerator ever built, has confirmed its predictions to 1 part in a billion. So when physicists say it is beginning to break, that statement does not arrive lightly. The Standard Model was assembled through decades of collaborative work in the middle of the 20th century, built piece by piece from theoretical predictions and experimental confirmations that accumulated across generations of physicists working on both sides of the theoretical and experimental divide. Every particle it predicted was eventually located in an experiment: the electron neutrino, the muon, the gluon, the W and Z bosons, the top quark, each prediction confirmed, one after another, over a span of decades. The final missing piece was called the Higgs boson, the particle tied to the mechanism that gives all other particles their mass. Scientists at the Collider confirmed its existence in 2012 after a search that had lasted nearly 50 years from the moment the particle was first theoretically proposed. The physics community celebrated. Every missing piece accounted for, every prediction confirmed. The framework was complete. Then the questions started, and they have not stopped since. The Standard Model works with extraordinary precision inside its own domain. Inside a laboratory, under controlled conditions, at the scales human instruments can currently probe, the model is essentially perfect. But pull back to the scale of the actual universe, and the failures arrive immediately, and they are not small failures. They are fundamental ones. The model says absolutely nothing about dark matter, the invisible substance that accounts for approximately 85% of all mass in the cosmos. This is not a minor gap. This is the model failing to describe the dominant component of all the matter that exists. It cannot explain dark energy, the force that is causing space itself to expand at an accelerating rate, a phenomenon confirmed by independent observations using multiple different methods. And it cannot answer what many physicists consider the deepest puzzle in all of science. Why does anything exist at all? According to the Standard Model, the Big Bang should have produced matter and antimatter in perfectly equal quantities. Every particle created alongside an antiparticle twin of opposite charge and equal mass. And when matter and antimatter meet, they annihilate each other completely, without remainder, converting entirely into energy. If the equations were correct, the universe should have destroyed itself in the first fraction of a second after it began. Everything cancelling everything else out, nothing left. A cosmos of pure diffuse energy dissolving into an empty vacuum. No stars, no galaxies, no planets, no atoms, no observers. You exist. That is the proof something went differently. The atoms in your body are made of matter. The air you are breathing is made of matter. Every star in every galaxy in the observable universe, every object that has ever been detected by any telescope or instrument pointed at the sky, is made of matter. Antimatter exists in tiny, fleeting amounts, created briefly in particle collisions and in certain radioactive processes, but immediately destroyed upon contact with the matter surrounding it. The universe is overwhelmingly composed of one type, and physics cannot tell you why. Something in the earliest moments of the universe tilted the balance. Matter won by a margin so thin it is almost impossible to express. For every billion antiparticles that existed in the first instant, there were 1,000,000,001 particles of ordinary matter. The billion pairs annihilated each other without trace. That single extra particle in every billion survived. And that fraction, that impossibly thin margin of survival, became every star ever formed, every planet ever assembled, every molecule in every living thing that has ever existed, anywhere in the observable universe. Everything you have ever seen, touched, smelled, tasted, or heard is made from those survivors. But the Standard Model cannot tell you what caused that margin. The answer lies somewhere outside the framework. This is not a new problem. Physicists have understood these gaps for decades. They have built extensions and added auxiliary theories, proposed corrections and modifications, and nothing has sealed the holes cleanly. And recently, something new appeared in the collision data. Particle behaviors that deviate from standard model predictions. Small deviations, barely measurable at current levels of precision, but appearing consistently across multiple independent experiments conducted under different conditions, and doing so in the same direction. Random errors scatter in all directions. Systematic signals point. The data is pointing. And scientists are now seriously discussing the possibility that the standard model is not just incomplete, but fundamentally wrong at scales smaller than any instrument has ever reached. That the universe is operating on a deeper set of rules hidden just below the current floor of human detection, where the standard model's equations give way to something more fundamental, something that would rewrite every physics textbook in existence and answer questions that have been sitting open for half a century. Finding those rules would represent the largest scientific breakthrough in human history, larger than the discovery of gravity, larger than the theory of relativity, larger than the decoding of the genetic code. And the search for them requires going somewhere no machine has ever managed to reach, to a scale of reality so small that everything you know about the physical world looks enormous by comparison. The morning of July 4th, 2012, began like any other at the facility outside Geneva. By that evening, it had become one of the most significant days in the history of science. In a packed auditorium, with physicists standing in the aisles and crowding the back of the room, a researcher walked to a podium and announced that after nearly 5 decades of searching, the Higgs boson had been found. One of the scientists in the audience began to cry. Another applauded until his hands went numb and red. Peter Higgs himself, the man who had first predicted the particle's existence back in 1964, was seated in the front row. He was 83 years old. He had spent his entire adult life waiting for this moment, reading papers written by other physicists about his prediction, watching experiments at accelerators across the world search for the particle with successively greater energies and successively greater sensitivity, and every time not finding it. Until that morning. The discovery was real. The particle was real. Its properties matched the predictions with remarkable precision. By any measure and from any angle, it was one of the great moments in scientific history, the culmination of 50 years of work by thousands of scientists across dozens of countries. The champagne was opened, the speeches were made, the papers were filed in the scientific journals, and almost immediately the celebration created a new and entirely unexpected problem. The confirmed mass of the Higgs boson came in at approximately 125 giga-electron-volts. For most people, that number means very little, but when you feed that specific value into the equations governing the stability of the vacuum of space, what comes back is not reassuring. The number sits in what physicists call the metastable region of the stability phase diagram. Not light enough for the vacuum to be completely and permanently stable. Not heavy enough for the vacuum to be obviously unstable and already in the process of collapsing. Right at the edge between the two. A middle state. A condition that can persist for an enormous length of time, potentially far longer than the current age of the universe, but which is not, strictly speaking, the lowest energy state available to the universe. Picture a ball resting in a shallow depression carved into the side of a long slope. The ball is still. It looks stable. It behaves as though it is going to stay there indefinitely. The depression keeps it in place through ordinary mechanics. But the depression is not at the bottom of the slope. It is partway up. And in the language of quantum mechanics, particles and fields do not actually need to be pushed over barriers in order to cross them. They can tunnel through, not metaphorically, not as an approximation, literally. Quantum tunneling is a real, measured, confirmed phenomenon. Fields that appear stable can spontaneously transition to lower energy states through this mechanism. The probability is very small for any given region of space in any given moment. But given enough time and enough volume of space, a transition that has any non-zero probability eventually happens. The universe may be sitting in that shallow depression. Physicists are careful about the language they use here. The timescales involved in any tunneling event, if the metastable picture is correct, are likely to vastly exceed the current age of the universe by many orders of magnitude. And the measurement uncertainties in the Higgs mass and in the closely related mass of the top quark mean that the picture could still shift toward full stability when better measurements arrive. The precise location of the universe on the stability map is not yet determined. But the principle is the thing. The particle physicists spent nearly 50 years hunting turned out to carry a mass that places the underlying architecture of reality in an uncertain zone, not clearly solid, not clearly hollow, somewhere in between, waiting for a measurement precise enough to resolve the question. The discovery of the Higgs boson, one of the greatest scientific achievements in human history, simultaneously opened a door onto one of the most uncomfortable questions physics has ever faced. And the discovery did not close a chapter. It opened several new ones at once. Because the Higgs field, the pervasive energy field that the boson is connected to, and that gives it physical meaning, is the mechanism by which every particle in existence acquires its mass. Remove the Higgs field from the universe, and every particle that currently has mass becomes massless. Massless particles travel at the speed of light. Atoms cannot form. Protons dissolve. Chemistry ceases to be possible. The universe as you experience it stops existing. The Higgs boson is the confirmation that this field is real, that it permeates all of space, that every electron and every quark in every atom of your body is interacting with it right now, continuously, and that this interaction is the source of the mass that makes you physically present in the world. But the field itself raises questions the standard model cannot answer, and has never been able to answer. Why does the Higgs field have the strength it has? Why does it give particles the specific masses they have, in the specific ratios they carry? Why is the electron's mass what it is, rather than 1,000 times larger or 1,000,000 times smaller? The equations contain these numbers. They confirm them to extraordinary precision. But they provide no explanation for them. To a physicist, an unexplained number sitting in the equations is not a complete answer. It is a signal that something deeper is missing. A sign that the framework is describing a consequence rather than a cause. That the true explanation for why these numbers are what they are lies at a scale of reality the current instruments cannot reach. Imagine standing in a commercial aircraft at cruising altitude, looking down at a city through patchy cloud cover. You can see the broad outlines of the urban structure, the pattern of major roads cutting through residential grids, the dark rectangle of a park, the silver line of a river bending through the urban fabric, the general shape of the coastline in the distance. From that altitude, the city looks complete, or at least substantially complete. You feel like you are seeing the main features of the thing. But now drop down, come into street level, and there is an entirely different world operating at a scale that was completely invisible from above. Conversations happening in doorways, a cafe with tables outside where people are arguing about politics, insects crossing the pavement on their own errands, cracks in the concrete following patterns that tell the story of decades of frost and thaw, a newspaper blowing down the gutter, details that were not just hard to see from the aircraft, they were literally below the resolution limit. The aircraft view was complete within its own limitations. It just had limitations you could not see from inside those limitations. Physicists believe something comparable is true of the universe at the fundamental level, that there is a layer of physical reality so deep, so unimaginably small, that the forces operating at that scale explain everything the standard model cannot. They have given this territory a name. They call it the zeptoscale. A zeptometer is 1/60th of a meter. Written out, that is a decimal point followed by 20 zeros and then a 1. The current collider can probe distances down to approximately 50 zeptometers already, which is itself far smaller than anything detectable by human senses, smaller than most molecules by a factor that is difficult to meaningfully express. But the zeptoscale proper, the territory physicists believe, contains the answers they are looking for, sits at 10 to the power of minus 21 meters, roughly 20 times smaller than the current machine can reach. No instrument built by human hands has ever gotten close to it directly. So why do physicists believe something important is happening there? Because when they work backward from the anomalies accumulating in the collision delta, when they calculate where the unresolved gaps in the standard model are anchored in energy and distance, when they trace the implications of the Higgs boson's mass through the equations, the mathematics keeps pointing to the same address. Something may be operating just below the current floor of human detection in ways that shape everything above it, like a foundation beneath a building that you have never been able to directly inspect, but whose presence you infer from the way the walls stand, the way the floors distribute weight, the way the structure behaves under stress. This is simultaneously the most exciting and the most frustrating frontier in modern physics. Exciting because the evidence suggesting something real is there has been accumulating from multiple independent directions. Frustrating because directly reaching that scale may require a collider many times more powerful than anything existing. Some of the proposals on the drawing boards describe a machine with a circumference approaching 100 kilometers, a ring that would encircle a major city, a project that would require generations of international coordination to fund and construct. So instead of looking directly at what might be there, researchers hunt for its signature in what they can see. If new particles or forces are operating at the zeptoscale, their presence will distort the behavior of known particles at detectable scales in measurable ways. The analogy physicists use is a familiar one from everyday experience. You can know that a stone has struck the surface of a lake you cannot directly observe just by watching the ripples travel outward to the shore. The stone is out of sight. The water it struck is out of sight. But the ripples are real. They are measurable, and from their pattern you can determine that something definite happened at the source. The strategy at the collider is to measure certain rare particle interactions with extraordinary precision. Any consistent deviation between the predicted outcome and the measured outcome becomes a signal from below, a ripple from a layer of reality the detector cannot directly photograph. There is a classic technique in physics that becomes important here. If you cannot observe something directly, observe what it does to everything around it. Nobody has ever photographed the singularity at the center of a black hole. What we observe are the jets of superheated material accelerating toward the event horizon. The bending of light around the gravitational well in a phenomenon called gravitational lensing. The strange and tightly constrained orbits of stars being whipped around something invisible but enormously massive. The black hole announces itself through its effects on the surrounding environment. Its presence is not in doubt for a moment, even though the object itself is invisible to every instrument we possess. The zeptoscale works the same way. Scientists at the collider cannot fire a beam at something 20 times beyond the resolution limit of their instruments. The physics will not permit it with current technology, So instead they have designed experiments that study specific particle interactions at accessible scales with a level of precision so extreme that any hidden influence from below would register as a measurable deviation in the outcome. The logic is clean and rigorous. If you know precisely how a particle should behave based on every known force and every known particle in the standard model, and you then measure its actual behavior not just once or 100 times, but hundreds of thousands of times under carefully controlled conditions, any consistent gap between the prediction and the measurement becomes a signal. A whisper from a layer of reality the detector cannot directly see. The entire challenge is building instruments sensitive enough to hear that whisper above the noise. The collider generates millions of particle collisions every second. The overwhelming majority of those collisions produce outcomes that are completely well understood, outcomes that physicists have mapped in exhaustive detail over decades of operation. But buried deep inside all those ordinary collisions are a handful of extraordinarily rare events. Interactions that the standard model says should almost never happen. Events so unlikely that across billions of collisions, only a few clean examples survive, the analysis cuts designed to isolate them. These rare events are the most sensitive instruments available to the experimenters. Because the rarer a process is, the louder any hidden influence sounds when it distorts that process. Think about it this way. A common process happening a billion times might shift by a few percent if something unknown nudges it. That few percent shift is hard to detect against all the other variations in a common process. But a rare process happening once in 10 billion collisions might double or triple its rate if the same unknown force pushes it. The signal from the same hidden physics is amplified dramatically, simply because the baseline rate is so low that any addition to it stands out clearly. The signal is louder on the rare events, even though the rare events themselves are harder to catch. This is the logic that makes the next generation of precision measurements so important, and it is the logic that makes one set of experiments in particular worth paying very close attention to right now. The physics community has started calling them the Magnificent Seven. 7 specific particle interactions. 7 ultra-rare decay sequences where the measurements keep coming back in a way that does not match what the standard model predicts. 7 sets of numbers that keep being slightly wrong, consistently slightly wrong, in the same direction, across independent experiments conducted by different teams, using different instruments, at different facilities in different countries. Each of the 7 involves particles built around quarks, the smallest known constituents of matter, breaking apart and transforming into lighter particles in specific sequences that the standard model can predict with remarkable precision, the key word being can, because the predictions and the measurements are beginning to diverge, not dramatically, not in ways that are obvious at first glance, but consistently, persistently, in a manner that physicists who work with this data every day find increasingly difficult to dismiss as noise. To understand why this matters, you need a mental image of what a particle decay actually is. Picture a radioactive material breaking down into lighter and more stable components over time. That breakdown follows rules. Specific products appear. They appear in specific proportions. They appear at specific rates that the underlying physics determines precisely. If you measured 1 million such breakdowns and found that the rates consistently came back different from what the rules predicted, not randomly different, not scattered equally in both directions around the predicted value, but consistently higher or consistently lower in a pattern that repeated across different experimental setups, you would conclude that something was influencing the process in a way the rules did not account for. That is precisely what the Magnificent Seven experiments are detecting. 2 of the 7 involve particles called B-mesons, which contain bottom quarks. Others involve D-mesons. 2 of the most sensitive involve a particle called the chion. and the Kaon experiments are currently producing the most striking hints of all. What makes these 7 specific interactions so powerful as detection tools is exactly their rarity. The standard model predicts them with exceptional precision because the rarer the process, the cleaner the theoretical calculation tends to be. So any deviation, even a small one, carries unusual weight. And several of the 7 are showing deviations in the same direction, across different teams, different experiments, different particle types. When multiple independent measurements all tilt the same way, physicists begin paying very close attention to what they are collectively pointing toward. You have never touched a quark. You have never seen one, felt one, held one, or isolated one in a laboratory. Despite being the fundamental building blocks of every proton and neutron in every atom of every object you have ever interacted with, quarks have never existed alone outside a particle collision for longer than a fraction of a milliseconds instant. They are permanently bound inside larger particles by forces so powerful that pulling 2 quarks apart does not free them. The energy you pour into the gap between them spontaneously generates new quarks to fill it. Trying to isolate a quark is like trying to cut a piece of rope and end up with nothing. You always end up with 2 shorter pieces of rope, each with their own ends. The harder you pull, the more energy you invest, and the more new quarks that energy creates. Quarks cannot exist in isolation. They are fundamentally social particles, always found in groups, always confined by a force that gets stronger the further you try to separate them from their partners. There are 6 types of quark, labelled by names that describe nothing physical about them at all. Up, down, strange, charm, bottom, top. The labels are arbitrary placeholders that physicists assign to 6 genuinely different objects with different masses, different charges, and different behaviours. The names came from a period in the history of physics when naming things after their properties had become unsatisfying, and the community collectively decided, more or less informally, to stop trying to make the names meaningful. Strange has no particular strangeness. Bottom is no more bottom than top is top. They are just 6 different things that needed 6 different labels. The strange quark, the 3rd lightest of the 6, was identified in the 1950s when physicists noticed that certain particles produced in cosmic ray collisions were living far longer before decaying than the strong nuclear force would have predicted. Something was slowing them down. Something was making them hesitate before breaking apart into lighter particles. This hesitation showed up consistently across different particle types and different experimental conditions. It was not a measurement error. Something was genuinely different about these particles. That strange, unexpected longevity gave the property its name, and eventually physicists traced the effect to the presence of a specific type of quark inside these particles. The strange quark, it turned out, can only decay through the weak nuclear force, which operates much more slowly than the strong force. That slow decay is why the particles containing strange quarks live long enough to leave detectable tracks in early particle detectors before disappearing. The strange quark is the key ingredient in kaons. A kaon is built from a strange quark paired with an up or down antiquark. When a kaon decays, the strange quark transforms through a sequence of interactions governed by the weak nuclear force, the force responsible for radioactive decay throughout the universe. The Standard Model describes this transformation in precise mathematical detail, accounting for every known particle and every known force that participates in or influences the process. The problem is that the mathematics and the measurements are starting to pull apart, not dramatically, but consistently. And in physics, consistent means something. Inside the collider, strange quarks do not decay in isolation. They interact with every known force and every known virtual particle that quantum mechanics permits to appear temporarily in the space around them. Quantum mechanics allows particles to pop in and out of existence in the vacuum for brief periods, borrowing energy from the uncertainty principle and returning it before the books can be balanced. These virtual particles are not hypothetical. Their effects are real, measured, and accounted for with extraordinary precision in standard model calculations. Physicists working on kaon decay rates account for every single one of these contributions. They have to, because the goal is to measure the final decay rate with enough precision that any leftover deviation, any rate that cannot be explained by every known contribution from every known particle and every known force, becomes direct evidence of something outside the current model. Something that the standard model does not know about and cannot predict. Strange quarks inside kaons are ideal for this search because their decay sequences involve processes that are extraordinarily rare, and rarity amplifies any hidden influence. A force too weak to measurably affect a common process might shift a rare one by a factor of 2 or 3, and the rates coming back from the kaon decay experiments at the Collider and at facilities across the world are not lining up with the predictions. The strange quark is responding to something that has no name in the current equations. The NA62 experiment does not look like the future of physics. It sits in a long, narrow hall inside a separate building within the Collider complex, away from the giant circular ring and the cathedral-scale detectors. There are no multi-story detector systems here, no towering magnets, no cavernous underground chambers, just a focused beam of kaons, a series of carefully arranged tracking sensors, electromagnetic calorimeters, and a team of physicists hunting for a specific decay so rare that even finding a small number of confirmed examples counts as a scientifically significant result in its own right. They were looking for a specific sequence, a positively charged kaon breaking apart into a positively charged pion, a neutrino, and an antineutrino. The standard model predicts this exact three-body decay should occur once in every 10 billion kaon decays. Once in 10 billion. To put that number in perspective, the odds of winning a major national lottery jackpot are roughly 1 in 300 million. This decay is 30 times rarer than winning the lottery, and scientists needed to detect it reliably enough to measure not just whether it happens, but how often it happens, and whether that rate matches the standard model's extraordinarily precise prediction for it. In 2024, the team published their result after years of data collection, analysis, and internal cross-checking. They had collected enough confirmed examples of this rare decay to produce a meaningful rate measurement, and the rate they measured was higher than the standard model predicted, not scattered randomly in both directions around the prediction as you would expect from statistical noise, consistently higher, pointing in the same direction as the other deviations accumulating across the Magnificent Seven experimental program. Here is why that particular result carries unusual weight even within a field full of precision measurements. The standard model calculates this specific kaon decay with some of the greatest precision achievable anywhere in all of physics. The calculation is clean in a technical sense that matters enormously. It involves a short-range quantum interaction, meaning that fewer of the complicated, difficult-to-calculate long-distance effects that cloud other measurements are involved. The dominant contributions to the decay rate come from physics at short distances, where the theoretical tools are most reliable and the systematic uncertainties in the calculation are smallest. Physicists trust this particular prediction more than almost any other in the entire model, which means that a deviation here carries more weight than a deviation in a measurement where the theoretical calculation has larger inherent uncertainties. Think of it like calibrating a measuring instrument. If you have a measuring tape that you have calibrated exhaustively against a known standard, repeatedly, under different conditions, and that tape has consistently given you correct readings for years, and then that tape gives you a reading for a new object that does not match the expected value, you do not immediately question the tape. You question the object. Something about it is different from what the theory told you to expect. The kaon is giving a different reading than it should. Something is influencing its decay rate. Either a particle too heavy to show up directly in the detector is acting as a hidden messenger, participating in the decay process from behind the scenes, or an undiscovered force is nudging the outcome in a direction the standard model does not account for, or something else entirely is happening that does not fit cleanly into either of those categories. None of these possibilities exists within the current framework. All of them would require physics beyond the standard model. The team was appropriately measured in how they announced the result. The deviation is real. The measurement is solid and has survived extensive internal scrutiny. But the statistical certainty required for a formal discovery claim in particle physics is very high by design, and the result sits just below that threshold. More data, more kaon decays, more events collected over additional years of running would push the significance level over the discovery bar or pull it back toward the prediction. The machine needs more runtime, which is exactly why a completely separate team on the other side of the world decided to push their own version of the experiment harder after hearing about the Swiss result. Roughly 10,000 kilometers from Geneva, inside a concrete building on a research campus in Tokai, Japan, a different group of physicists is running a different version of the same hunt. The experiment is called KOTO. It targets the neutral kaon, the uncharged version of the same particle the Na-62 team in Switzerland has been studying. Neutral kaons decay differently from charged ones in ways that matter for this kind of search. The specific decay sequence KOTO is measuring is even rarer than the one Na-62 studied. The standard model predicts it should occur roughly 3 times in every 100 billion neutral kaon decays. 3 times in 100 billion. This is not a number that translates easily into any everyday comparison. Finding even a single confirmed example of this event in a reasonable period of running is considered a genuine achievement. Finding enough confirmed examples to build a reliable rate measurement is a years-long undertaking that requires extraordinary experimental control over every possible source of background contamination. The question of why you would build 2 separate experiments chasing essentially the same type of rare event on opposite sides of the planet is a question with a direct answer. Independent confirmation is the most powerful tool science has ever developed. History is full of signals that turned out to be noise. Instrument errors that looked exactly like discoveries until a second experiment checked and found nothing. Statistical fluctuations that appeared compelling in a small data set and vanished when more data arrived. The scientific community learned this lesson the hard way through multiple high-profile false discoveries across the 20th century, and the response was a culture of intense, institutionalized skepticism toward any single result, however clean and however compelling it appears when first announced. If 2 completely independent experiments, using different instruments, different kaon types, different analysis methods, different systematic uncertainties, and different physics teams in different countries, arrive at consistent deviations from the same standard model prediction, the probability that both results are wrong in the same direction, purely by coincidence, approaches 0 in a way that is mathematically quantifiable and genuinely compelling. KOTO has been running since 2013, and its results have been a sustained source of tension and careful excitement in the physics community. In 2019, the team announced a preliminary result showing more events than the standard model predicted. Papers from theorists flooded in within weeks, exploring what kind of new particle or new force could explain the excess. Then further analysis revealed that some of the excess might be partially explained by background events that had not been fully accounted for in the initial analysis. The The excitement cooled, but the mystery did not disappear. The hunt continued with upgraded detectors and refined analysis methods. As the NA62 team in Switzerland published their higher-than-predicted rate in 2024, COTO's newer and larger dataset is being analysed with those results in mind, with the benefit of knowing what direction any real signal should be expected to point. Two experiments converging on the same territory from opposite sides of the planet, using different kaon charges, different detector technologies, different systematic uncertainties. If both consistently land above the standard model's prediction for the same underlying physics process, the case for something new becomes very difficult to set aside. The theoretical explanations being seriously considered range from new heavy particles that mediate interactions the standard model does not include, to extensions of the Higgs sector involving additional Higgs-like particles with different couplings, to entirely new symmetries of nature operating at the zepto scale. Each possibility, if confirmed, would trigger a fundamental restructuring of particle physics, and each touches on the deepest question connecting all of these experiments together. Why does matter exist at all, and why didn't it destroy itself before the universe had a chance to form anything? Galaxies should fly apart. That is the conclusion you reach when you do the calculation carefully. Take a typical spiral galaxy like the Milky Way. Add up all the visible matter you can detect. Every star, every gas cloud, every dust particle, every object that emits or reflects or absorbs electromagnetic radiation in any way detectable by any telescope. Calculate the total gravitational pull that mass generates at different distances from the galactic center. Then measure the actual orbital speeds of stars at different distances from that center, the speeds at which they are actually moving through space as they orbit around the central mass. The maths does not work. The outer stars are moving far too fast. At the speeds they are actually observed to be traveling, the gravitational pull from all the visible matter combined should be completely insufficient to keep them in orbit. They should have escaped into the intergalactic void long ago, leaving the visible galaxy behind. But they have not. They are still there, tracing their orbits faithfully, as though being held by a gravitational field much stronger than the visible mass alone could produce. Not just in one galaxy, not in a handful of unusual cases. In every galaxy that has ever been studied in sufficient detail to perform this calculation. The pattern is universal. Something is providing the additional gravitational pull, something with mass, something that does not emit light, does not reflect light, does not absorb light in any way any telescope ever constructed can detect. Something completely invisible to the electromagnetic spectrum across every wavelength from radio waves to gamma rays. Physicists call it dark matter. And the number should stop you. Dark matter accounts for approximately 85% of all mass in the universe. The stuff you can see, every star, every planet, every gas cloud, every atom that has ever been measured by any instrument, is only 15% of the total mass that exists. The dominant component of the universe is something humanity has never directly detected. That is not a theoretical preference or an interpretation of ambiguous data. It is the conclusion forced by multiple independent lines of evidence, each of which points to the same result. The evidence for dark matter comes from multiple independent directions, which is why it is taken so seriously. The galaxy rotation problem is the most commonly cited, but it is far from the only one. Gravitational lensing provides a completely independent line of evidence. Light bends around massive objects due to general relativity, and observations of distant galaxy clusters show light bending around regions of space that appear to contain essentially no visible matter at all, curving as though around something massive and unseen. The structure of the cosmic web, the the vast network of filaments and sheets and voids that organizes galaxies and galaxy clusters across the observable universe, only makes mathematical sense if enormous quantities of dark matter were present in the very early universe to act as a gravitational scaffold around which ordinary matter could collect and condense. The cosmic microwave background, the faint radiation left over from the early universe that has been mapped with extraordinary precision, carries patterns in its temperature fluctuations that match dark matter models with remarkable specificity and that do not fit any explanation that leaves dark matter out. Everywhere physicists look, the fingerprints of dark matter are present, and the particle itself has never appeared in any detector. That absence is becoming an increasingly serious problem, not because it means dark matter does not exist, but because it means every naive expectation about where to find it has turned out to be wrong, and the search is having to evolve accordingly. Physicists had good theoretical reasons to expect dark matter particles to appear in collider experiments. Many of the most popular theories predicted that dark matter should be created in high-energy collisions and then escape the detector without interacting with it, leaving a distinctive signature in the form of missing energy and momentum that the detected particles alone cannot account for. The collider searched for exactly this signature during its first run. Nothing. A second run at higher energy searched again with greater sensitivity. Nothing. Current experiments continue the search at still higher precision. The silence is not proof the particle is not there. Detection of a particle that barely interacts with anything is extraordinarily difficult, and absence of evidence is not the same as evidence of absence when the sensitivity of your search instrument is the limiting factor. But the silence is forcing physicists to consider alternatives they were initially reluctant to take seriously, including possibilities that would require revising not just the inventory of known particles, but the foundational framework of how gravity itself is described. Several researchers have proposed that the gravitational anomalies attributed to dark matter might instead indicate that our description of gravity at very large scales is incomplete. That Einstein's general relativity, while essentially perfect within the solar system and in the vicinity of compact objects like neutron stars and black holes, might need small modifications at the very low accelerations that describe the gravitational dynamics of galaxy outskirts. This idea connects to the dark matter problem and to the kaon anomalies in ways that theorists are beginning to take seriously. The invisible majority of the universe and the strange behavior of a particle, a billionth of a meter across, may be symptoms of the same missing physics. That connection, if it turns out to be real, would represent one of the most profound unifications in the history of science. At the moment of the Big Bang, matter and antimatter were created in equal quantities. Every particle alongside an antiparticle twin, every electron next to a positron, every proton beside an antiproton, every quark partnered with an antiquark. The symmetry was exact, or should have been, and when matter meets antimatter, both annihilate completely, converting their combined mass into energy without remainder. If this symmetry held perfectly in the first moments of the universe, the mutual annihilation should have been total, everything cancelling everything else out, right down to the last particle, the last antiparticle, the last pair. A universe of pure radiation, expanding and cooling, with no matter left to form atoms, no atoms left to form stars, no stars left to synthesize the heavier elements, no heavier elements left to build planets, and no planets or chemistry or biology anywhere in the cosmos. Instead, here you are. Every atom in your body is a survivor. Every atom in the chair beneath you, in the walls around you, in the atmosphere above you, in the sun burning in the sky, is a survivor from the original asymmetry. Something in the first moments of the universe introduced a tiny imbalance. matter won over antimatter by a margin of approximately 1 part in a billion. For every billion particle-antiparticle pairs that annihilated each other, there was one extra particle of ordinary matter left over. That 1 in a billion surplus became everything. Physicists call the process that created this imbalance baryogenesis, the mechanism that shifted the balance from perfect symmetry to a universe dominated by matter. And despite decades of serious theoretical and experimental effort, no satisfying explanation exists. The Standard Model does contain a small asymmetry between how matter and antimatter behave, an asymmetry called a charge parity violation. The first experimental hints of it appeared in the 1960s, discovered initially through studies of kaon decays. Different types of kaons were found to decay at slightly different rates depending on whether they contained matter or antimatter components. This tiny asymmetry was the first experimental evidence that the universe does not treat matter and antimatter with perfect symmetry. But the asymmetry measured in the Standard Model is far too small, by a factor of many billions. The tiny imbalance that current physics accounts for could not have produced a universe dominated by matter. Something much larger shifted the balance in the first moments after the Big Bang. Something outside the Standard Model. The Magnificent Seven experiments are partly a search for exactly this missing piece. If new particles or new forces are influencing the decay rates of kaons and B-mesons in ways the current model does not account for, those same new forces might carry a larger charge parity violation than anything in the Standard Model, large enough to explain why matter survived. The existence of stars and planets and chemistry and biology and conscious observers is the direct consequence of matter winning that original contest by a fraction. Finding the mechanism that produced the victory would be among the most profound answers in the history of human inquiry. At the moment, 2 proton beams collide inside the Large Hadron Collider. Something extraordinary unfolds on a timescale so short that no clock ever built could measure it. Hundreds of new particles spray outward in every direction from the collision point. They reach the surrounding detectors in less than a billionth of a second. Each particle leaves a distinct signature as it passes through different layers of the instrument. Charged particles curve in the intense magnetic field threaded through the detector volume. Some particles deposit energy in characteristic ways in the layers of dense material designed to absorb them. Some pass through certain layers and stop, depositing all their energy in a measurable pulse. Some pass through everything, interacting with essentially nothing, and are only detectable by the momentum imbalance they leave behind in the event. A single collision lasts a fraction of a second, and the collider produces roughly 40 million of them every second, all of them happening simultaneously around the ring at 4 separate collision points. The 2 largest detectors are called Atlas and CMS. They sit at opposite points around the ring, each surrounding a collision point and recording the aftermath of every event that passes the trigger selection criteria. Both are built like enormous multi-layered spheres, with each concentric layer designed to detect a specific class of particle or measure a specific property of the particles passing through it. The CMS detector alone weighs 14,000 tons. Its central component is a superconducting solenoid magnet, generating a field strong enough to bend the trajectories of particles moving at near light speed, allowing physicists to measure their momentum from the curvature of their paths. Without the ability to measure momentum, the physics analysis becomes impossible. Inside CMS are thousands of crystals made from lead tungstate, a material that presents one of the most counterintuitive combinations of physical properties of any substance ever manufactured. Completely transparent to visible light, something you could hold up and look through like colored glass, yet roughly 8.5 times denser than water and significantly heavier than solid iron. When a particle strikes one of these crystals, It flashes with a burst of blue and ultraviolet light. Sensitive electronic sensors positioned around each crystal capture that flash and convert it into a digital signal within nanoseconds. The pattern and intensity of thousands of these flashes, assembled and analyzed in microseconds, tell physicists what particles emerged from the collision and how much energy each one carried away from the interaction point. The detectors process 40 million collision events per second. The raw data volume this generates is completely unmanageable by any computing infrastructure that exists or is likely to exist in the foreseeable future. The facility produces over 90 petabytes of data annually from the events that survive the filter alone. A single petabyte is roughly equivalent to 10 billion smartphone photographs. 90 petabytes is 900 billion photographs. A sophisticated real-time filtering system called the trigger evaluates every collision the instant it happens, using fast electronic circuits and embedded processors to assess the initial detector signals, identify whether the event has features consistent with theoretically interesting physics, and either flag it for full recording or discard it permanently within a few microseconds. Most events are discarded. The machine is designed to do this because saving everything would require a data pipeline orders of magnitude larger than anything currently feasible. The trigger is programmed to look for signatures that match theoretically motivated event types. Specific patterns of particle tracks, unusual energy distributions, missing momentum signatures that might indicate a particle escaped the detector without interacting. Rare kaon decay patterns are on the trigger priority list. This creates a philosophical tension that physicists openly discuss in workshops and review papers. If something genuinely unexpected appears in the data but does not match any pattern the trigger was programmed to recognize, the event is deleted before any human or computer analysis system ever sees it. The trigger is designed around current theories. It is, at some level, looking for what physicists already expect to find, with variations. Something completely outside the theoretical framework might be systematically discarded by a filter that does not know to keep it. Researchers are aware of this problem and work continuously to make the trigger criteria as broad as the available bandwidth permits. But the fundamental constraint does not go away. You cannot save everything. You have to make choices about what to keep before you know what you are looking for. This is one of the inescapable tensions at the frontier of experimental physics. Even in the underground tunnel, sealed from the surface by 100 meters of rock, one aspect of the physical environment causes a problem that engineers discovered with some surprise in the early years of operation. The moon. The tunnel is sealed. The machine operates in a vacuum colder than outer space. The beam pipes are isolated from vibrations. The entire facility is designed to separate the experiment from the surrounding environment as completely as engineering allows. And yet twice a day, the position of the moon in its orbit shifts the path of the proton beams measurably. The shift is small. The displacement is measured in fractions of a millimeter. But fractions of a millimeter matter enormously when you are trying to steer two beams of protons traveling at 99.9% of the speed of light through a pipe less than 10 centimeters across, aiming them at a collision point that needs to be reproduced to microscopic precision millions of times per second. The effect is gravitational. As the moon moves through its orbit, its gravitational pull causes the Earth's crust to flex very slightly. The rock beneath the surface experiences what geologists call earth tides, a slow rising and falling of the ground surface by a few centimeters twice a day as the crust responds elastically to the changing gravitational field. The 27-kilometre tunnel that houses the accelerator sits in this rock. As the rock flexes, the tunnel flexes with it. The precisely engineered circular geometry of the ring changes shape slightly, twice every day, in a pattern that follows the lunar orbital period exactly. Engineers at the facility discovered this effect during early operations when they noticed that the beam required constant small corrections at a rhythm that matched the lunar cycle. Once they understood the cause, they built correction systems to compensate. Today, the control systems monitor beam position continuously and apply thousands of tiny magnetic corrections every second to keep the beams on the intended path, with part of those corrections accounting specifically for the tidal deformation of the tunnel caused by the Moon's gravity. The same gravitational force that moves the world's oceans is being actively corrected for in real time inside a particle accelerator 100 meters underground. This is one of those details that does something to you when you sit with it. The most precise physics experiment in the history of science cannot operate without accounting for the gravitational influence of an object 384,000 kilometers away. Everything in the universe is connected to everything else, right down to the path of a proton beam in a tunnel beneath European farmland. The water level in Lake Geneva, several kilometers from the facility, also changes seasonally, redistributing mass in ways that alter the local gravitational field by a tiny but measurable amount. The passage of trains in the Geneva suburbs was tracked during the early years because the vibrations they generated in the rock could theoretically affect beam stability. At this level of precision, the entire physical environment around the experiment must be understood, modeled, and corrected for. The same precision that requires lunar corrections is the same precision that makes a deviation of a few percent in a rare kaon decay rate worth treating as a potential signal from beyond the standard model. The beam pipes carrying the protons contain one of the most complete vacuums ever created on Earth. The pressure inside is roughly 10 times lower than the pressure on the surface of the Moon, which has essentially no atmosphere. This near-perfect vacuum is not an engineering nicety. It is a fundamental requirement. A proton, moving at 99.9% of the speed of light, carries enough kinetic energy that a collision with a stray gas molecule would scatter it completely off course, destroying the carefully maintained beam structure. To keep hundreds of billions of protons traveling in two tightly controlled beams for hours at a time, the tube they move through has to be as close to perfectly empty as engineering can achieve. Creating that vacuum requires pumping systems distributed along the entire length of the 27-kilometer tunnel, running continuously throughout every physics run, fighting the slow outgassing of molecules from the walls of the metal beam pipe. The magnets surrounding those near-empty pipes operate at -271 degrees Celsius. This temperature is achieved and maintained by liquid helium cooling systems that represent one of the largest cryogenic installations ever built. At this temperature, the electrical resistance of the superconducting magnet coils drops to essentially zero. Current flows through the coils without energy loss. This is what makes it possible to generate the magnetic field strong enough to bend near light-speed protons around a 27-kilometer circle. At room temperature, the electrical power required to generate equivalent fields would be physically impossible to supply continuously. The machine therefore exists in two extreme states simultaneously. Beam pipes emptier than the surface of the Moon. Magnets colder than the outer planets. And at the moment of collision, a temperature reached at the collision point of nearly 10 trillion degrees. The core of the Sun reaches approximately 15 million degrees. The collision point inside the collider is roughly 650,000 times hotter than that. At these temperatures, protons dissolve into the quarks and gluons that make them up. Those quarks and gluons join a brief expanding plasma called the quark-gluon plasma, a state of matter that last existed naturally in the universe in the first microseconds after the Big Bang, before the universe had cooled enough for quarks to recombine into protons and neutrons. That plasma persists for an almost unmeasurably short time before cooling and recombining into the particles that spray outward into the detector. From cold vacuum to 10 trillion degrees and back, in a region smaller than an atomic nucleus, in a time shorter than any clock can measure. And buried in the patterns of what comes out, in the decay sequences of the rarest particles produced, are the hints that the standard model may have reached the boundary of its validity. The universe feels stable. Stars burn on timescales of billions of years. Atoms hold together across geological time. The laws of physics appear identical whether measured in a laboratory on Earth or inferred from light arriving from galaxies 12 billion light-years away. Every observation and every experiment points to a cosmos built on a solid and consistent foundation. But there is a calculation that physicists keep returning to, based on the confirmed mass of the Higgs boson combined with the best available measurement of the top quark's mass, that produces a result that is genuinely uncomfortable to sit with. The calculation concerns the energy state of the vacuum of space itself. In quantum physics, the vacuum is not empty in the way an empty room is empty. The vacuum is a seething, dynamic medium filled with quantum fields whose values fluctuate constantly, with particles blinking in and out of existence for tiny fractions of a second before annihilating back into the vacuum, with energy present in every cubic centimetre of apparently empty space. Every field permeating the universe has an energy state, and the lowest possible energy state that a field can occupy is called the true vacuum. A field not sitting at its absolute lowest energy is sitting at a higher energy state called a false vacuum. It can remain in that false vacuum for an enormous length of time. It can look completely stable for all practical purposes, but it is always technically at risk of making a quantum transition to the true ground state, a transition that requires no external trigger and follows no predictable schedule. Run the equations using the Higgs boson's confirmed mass of approximately 125 giga-electron volts, combined with the best current measurements of the top quark mass, and the calculation places our universe in the metastable region. Not in the fully stable zone, not in the unstable zone where the vacuum would have already collapsed long ago. In the middle zone. The zone where the vacuum appears stable and can remain so for an almost inconceivably long time, but is not at the absolute lowest energy state available to it. Think of a ball resting in a shallow depression carved partway up the slope of a long hillside. The ball is still. It looks stable. It has been sitting in that depression for a very long time and will continue to sit there for a very long time to come. The depression is real. The stability is real in a practical sense. But the depression is not at the bottom of the hill. There is a lower state available. The ball is not there. In quantum mechanics, barriers between states can be tunneled through without the system being given any external energy. The probability for any given small region of space to undergo such a tunneling event at any given moment is extraordinarily small. But given enough time, in a universe large enough and old enough, events with any non-zero probability eventually occur. Physicists who study this scenario are not predicting imminent catastrophe. They are not suggesting the universe is about to transition. The timescales involved are likely to vastly exceed the current age of the universe by many orders of magnitude. And crucially, the calculation is sensitive to the exact values of the Higgs mass and the top quark mass, both of which carry measurement uncertainties that currently straddle the boundary between stability and metastability. Improve those measurements enough and the picture might shift to full stability. But it might not. And that uncertainty is itself the thing worth understanding. A vacuum collapse would be unlike any other event in the history of the cosmos. Not a catastrophe in any ordinary sense. Not an explosion that destroys and leaves wreckage. A conversion. A bubble of true vacuum would nucleate at some point in space, some region where the quantum tunneling event occurred, and that bubble would begin expanding outward in every direction at the speed of light. The bubble wall itself is a boundary between two versions of physics. Inside the bubble, the Higgs field has settled into its true minimum energy state. The value of the field inside the bubble is different from the value outside it. That difference means the masses of all particles inside the bubble are different from their masses outside it. The strengths of the fundamental forces inside the bubble are different. The relationships between particles and fields that allow atoms to form, that allow chemical bonds to hold, that allow stars to burn through nuclear fusion, are all different inside the bubble from what they are outside it. Matter as it currently exists, built around atoms with the specific masses and interactions they carry in our universe, would cease to be viable inside the expanding region, and the expansion would proceed at the speed of light. This is important. The speed of light is the maximum speed at which any information can travel. The bubble wall, expanding at that limit, is invisible in front of it. Nothing can travel faster than the light that would carry advance warning of the bubble's approach. If such a transition occurred in a galaxy 1 million light-years away at this moment, the bubble front would arrive at Earth in 1 million years, traveling at the maximum possible speed, with no precursor signal of any kind running ahead of it. The transition when the wall arrived would be instantaneous from any observer's perspective. One moment, the physics you have always existed inside. Then the physics ends. This is the scenario that physicists are careful to contextualize. The probability is extraordinarily low. The timescales are vast. The measurement uncertainties leave the door open to full stability, and the collider itself poses no risk, as the energy densities in the most extreme collisions are dwarfed by cosmic ray events that bombard every object in the universe continuously. If collider-scale energies were sufficient to trigger a vacuum collapse, cosmic rays would have triggered one long ago, and the age of the universe is the evidence that they have not. What the machine can do is pin down the Higgs mass and the top quark mass with increasing precision, and in doing so locate the universe more accurately on the map between stability and metastability. One additional decimal place on a particle's mass, measured 100 meters underground, potentially determining whether the ground floor of reality is solid. In 2026, the machine goes dark. The proton beams are switched off for the last time in this operational period. The cryogenic cooling systems that have kept the magnets at -271 degrees Celsius are carefully and slowly warmed, a process that itself takes weeks. Thousands of engineers, technicians, and specialists from dozens of countries enter the 27-kilometre tunnel, carrying equipment, tools, replacement components, and years of accumulated maintenance and upgrade plans. Long Shutdown 3 is not a maintenance interval. It is the most ambitious transformation the facility has undergone since it was first commissioned. The goal is to rebuild every component that currently limits the number of collisions the machine can deliver per second. The magnets nearest the 4 collision points around the ring will be replaced with a new generation of superconducting focusing magnets built using a material called niobium tin, an alloy that can carry significantly higher electrical currents than the niobium titanium used in the original machine. Higher current means stronger magnetic field. Stronger field means the proton beams can be focused into a tighter cross-section at the collision point. A tighter beam cross-section means more protons pass through the same microscopic collision zone in each crossing of the beams, which means more actual collisions per second. More collisions per second is the entire objective of the upgrade. Niobium tin is harder to work with than the original magnet material. It is more brittle. It is more sensitive to mechanical stress during fabrication. Bending it into the precise coil geometries required for high-field focusing magnets required the development of new fabrication techniques at facilities across the world, techniques that did not exist when the original machine was designed. Hundreds of these new magnets have been built over several years and will be installed during the shutdown. The innermost detector layers at the two largest experiments are also being completely rebuilt. These layers, the ones closest to the collision point and therefore exposed to the most intense radiation from millions of collisions per second, accumulate radiation damage over time that gradually degrades their spatial resolution. The upgrade installs new silicon pixel detectors capable of operating at the higher radiation levels the upgraded machine will produce. New electronics throughout both major experiments will handle a trigger and data rate 10 times higher than the current systems manage. The shutdown is scheduled to run until approximately 2029. 3 years of coordinated construction work inside a tunnel that requires specialist training simply to enter, involving teams from dozens of countries working in parallel on thousands of separate tasks. When the machine restarts and the first upgraded beams circulate, the physics program will have access to a collision rate categorically different from anything that existed before. The High Luminosity Large Hadron Collider is the name for the upgraded machine. It is scheduled to begin delivering physics quality data around 2029. At that point, the collision rate will be 10 times higher than the current machine's peak performance. Not 10% higher, not twice as high, 10 times. Billions of collisions every second sustained across years of continuous operation. The physics case for this increase is direct and quantifiable. Every rare process the experiments study improves in statistical precision as the number of observed examples grows. A signal appearing at 2 standard deviations of significance in the current dataset, enough to be interesting and worth paying attention to, but not enough to be convincing, reaches 5 standard deviations after years of running at 10 times the collision rate if the signal is real. 5 standard deviations is the threshold the particle physics community uses for claiming a discovery. The probability of a result at that significance level arising from random statistical fluctuation is less than 1 in 3 million. The threshold is deliberately demanding, set at this level specifically because the history of the field includes multiple high-profile false discoveries that generated enormous excitement and theoretical activity before dissolving when more data arrived. The kaon anomaly from NA62, the B meson rate deviations from multiple experiments, the Higgs mass sitting near the stability boundary. Every one of these gets pushed across or firmly away from the discovery threshold once the upgraded machine runs at full luminosity for several years. The upgrade also reaches into regions of physics currently invisible to the existing machine. There are particle mass ranges that the current collider can in principle produce particles in, but cannot study with sufficient statistics because the collision rate is not high enough to accumulate a meaningful sample of the extremely rare events involved. The high luminosity upgrade pushes these regions into full statistical view. A particle produced once in every 10 billion collisions at the current machine becomes observable in a statistically significant sample after years of running at 10 times the rate. Dark sectors that are currently just barely hinted at in the data become accessible territory. The kaon and B meson anomalies, if real, become confirmed discoveries. If not real, they fade definitively into the noise and the search moves elsewhere. Either outcome eliminates the current ambiguity. And eliminating ambiguity is one of the most valuable things a physics experiment can do. There are regions of physics the current detectors can sense but cannot clearly examine. Physicists call them dark sectors. The phrase covers a collection of theoretical possibilities describing physics that operates outside the known particles and forces of the standard model, but at energy scales the collider can actually reach if the collision rate and detector sensitivity are high enough. The word dark here does not mean dark in the visual sense. It means hidden, decoupled from ordinary matter. interacting with the particles and forces we know about so weakly that those interactions barely register in any detector built to study ordinary physics. The search for dark sectors looks different from hunting a new heavy particle that decays quickly into well-understood final states and lights up the detector in a clear pattern. Dark sector particles, if they exist, might travel measurable distances before decaying, because their weak coupling to ordinary matter means they live longer before interacting. Their decays might produce combinations of particles that are harder to distinguish from ordinary background processes. They might produce what experimenters call displaced vertices, meaning the decay happens not at the original collision point where the particle was created, but at a measurable distance away from it, inside the body of the detector. One specialized experiment at the facility, called phaser, sits in a narrow tunnel more than 450 meters from the main collision point. It is designed to catch particles so weakly interacting that they travel the entire length of the facility from the collision zone and only decay inside the small detector positioned at the far end. Finding even a handful of such events would constitute evidence of physics operating in a dark sector. Another dedicated detector looks specifically for neutrinos produced in the highest energy collisions, capturing them as they interact in a dense block of tungsten positioned along the beam axis. Neutrinos are in some sense the archetypal dark sector particle, interacting with ordinary matter so feebly that trillions of them pass through your entire body every second without touching a single atom. Studying neutrinos produced directly in the highest energy collisions ever achieved allows physicists to test whether their behavior matches standard predictions or shows signs of mixing with hypothetical heavier partners. These heavier partners, sometimes called sterile neutrinos, are among the most compelling candidates for both dark matter and for the additional charge parity violation needed to explain why matter survived the Big Bang. Finding them would simultaneously explain why ordinary neutrinos are so astonishingly light and provide the missing ingredient in the matter-antimatter asymmetry story. Two of the deepest open problems in physics, connected by a single proposed particle that no experiment has yet confirmed. Dark sectors represent the possibility that the universe contains entire categories of particle and force that are physically present and causally important, but essentially transparent to everything we have ever built to detect them. The matter you are made of, the light you see by, the forces that hold your atoms together, might all exist in a small bright corner of a much larger physics that operates mostly in the dark. Every second, approximately 100 trillion neutrinos from the sun pass through your body. 100 trillion. Not 100, not 100 million, 100 trillion, every second, without pause, around the clock. They enter from above through the roof, pass through your skin and organs and bones, as though those structures are not there at all, and exit through the floor below you. Your body is as transparent to them as a pane of glass is to visible light. So is the Earth. A neutrino moving at near light speed can pass through a block of lead 1 light-year thick and have roughly even odds of interacting with a single atom during that entire journey. This near-total invisibility made neutrinos one of the most frustrating particles in the history of physics to work with. They were first proposed theoretically in 1930 by physicist Wolfgang Pauli, who introduced them to solve a crisis in the understanding of radioactive beta decay. Energy appeared to be disappearing in beta decay processes in ways that violated conservation of energy, one of the most fundamental principles in all of physics. Pauli proposed that an unknown particle was carrying the missing energy away undetected. He was acutely aware of how unsatisfying this proposal was. He had invented a particle specifically to escape a measurement problem, a particle so undetectable that he initially believed it might never be directly confirmed experimentally. He very nearly apologized in the original letter proposing the idea. He suggested the neutrino existed, but was not sure science would ever be able to prove it. He was wrong about that. Neutrinos were experimentally confirmed in 1956, 26 years after Pauli proposed them, using a detector placed close to a nuclear reactor where the flux was high enough that occasional interactions with detector material became measurable. Since then, physicists have established a great deal about neutrinos. They come in three types called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. As they travel through space or matter, they oscillate between these flavors in a quantum mechanical process that has been confirmed by multiple independent experiments. An electron neutrino produced in the Sun's core may arrive at Earth partially converted into a muon neutrino. This oscillation was experimentally confirmed, and the discovery was awarded the Nobel Prize in Physics. But the oscillation itself proved something the original Standard Model had assumed to be false. Neutrinos have mass. The original model assigned them exactly 0 mass. Oscillation between flavors requires mass. A massless particle cannot oscillate. The Standard Model had to be extended to accommodate this confirmed observation. This extension is a source of genuine theoretical discomfort. The mass of neutrinos, while confirmed beyond any doubt, is extraordinarily small, millions of times lighter than the electron, which is itself the lightest known massive particle. No mechanism in the Standard Model naturally produces a mass this small without what physicists consider severe fine-tuning, essentially adjusting parameters by hand to extreme precision to reproduce a result that the theory provides no underlying reason for. The leading explanation for why observable neutrino masses are so tiny is called the seesaw mechanism. The observable neutrinos we detect are light because they are partnered with an extremely heavy version, a sterile neutrino, and the two types are related by a mathematical relationship in the equations such that the product of their masses is approximately fixed. The heavier the sterile neutrino partner, the lighter the observable one. This seesaw relationship naturally produces an observable neutrino that is very light if the sterile partner is very heavy, and the required heaviness places sterile neutrinos in mass ranges potentially accessible to the collider. If sterile neutrinos exist in the right mass range, they would occasionally be produced in high-energy collisions. They would then travel invisibly through the detector, because they interact almost not at all with ordinary matter. But their existence would manifest as missing energy and momentum in the collision products. And if they decay inside the detector, which they might do for certain mass values, the decay products would appear at a displaced location away from the original collision point, a distinctive signature that would be very difficult to explain as anything other than a new particle. Finding sterile neutrinos would simultaneously explain the lightness of observable neutrinos through the seesaw mechanism, potentially supply the additional charge parity violation needed to explain why matter survived the Big Bang through a process called leptogenesis, and potentially account for some fraction of the dark matter. 2 or possibly 3 of the deepest open questions in physics, connected by a single undiscovered particle. Running the most complex machine ever built by the human species consumes approximately 1.3 terawatt-hours of electricity every year. That is enough to power a city of roughly 300,000 people around the clock. During peak physics runs, the demand rises higher still, and the facility coordinates with regional electrical grid operators to manage the draw without destabilizing the surrounding power infrastructure. Nearly every component of the machine either requires enormous power to operate or requires enormous power to maintain at the conditions it needs to function. The superconducting magnets need continuous liquid helium refrigeration to stay at -271 degrees Celsius. The cryogenic systems generating that refrigeration are themselves massive engineering installations, consuming significant power around the clock. The radio frequency cavities that accelerate the proton beams on every circuit of the ring use high-power radio waves to push the protons forward, adding a small increment of energy with each pass through the cavity. These cavities consume substantial power continuously throughout every operational period. The computing grid that processes and stores 90 petabytes of data annually runs without pause at dozens of sites worldwide. The facility has pursued efficiency improvements in the cryogenic systems, the computing infrastructure, and the accelerator systems across successive operational periods, and the high luminosity upgrade includes provisions for more energy-efficient magnet cooling designs. But the fundamental physics of what the machine does, generating the highest energy particle collisions ever achieved by any technology, cannot be made low power. There is no shortcut. The energy required to probe the structure of matter at these distances is determined by quantum mechanics and is not negotiable. The antimatter produced at the facility over its entire operational history provides a striking illustration of the energy economics of fundamental physics. If you collected every antiparticle ever created in every experiment at the facility across all years of operation, every antiproton, every positron, every antihydrogen atom, and annihilated them all simultaneously with an equal quantity of ordinary matter, the total energy released would not power a single incandescent light bulb for a meaningful period of time. The quantities involved in particle physics experiments, while individually enormous in terms of energy density, are microscopically tiny in terms of total energy when compared to the scales of everyday human experience. This is the regime where physics operates when it is probing the deepest levels of the structure of matter. Extraordinary sensitivity, microscopic signals, and machinery of immense scale, complexity, and cost required to reach them. Particle physics has a word for the kind of result that generates excitement before disappearing, a 3 sigma result. In statistics, sigma measures how far a measurement sits from the expected baseline value in units of standard deviation. A 3 sigma result means the measurement sits 3 standard deviations away from the prediction. This sounds like a large deviation, but it occurs by pure chance in roughly 1 out of every 300 measurements, even when no real signal is present. 3 sigma results have a problematic history in particle physics. In the early 2000s, several experiments reported 3 sigma hints of new particles that vanished without trace when more data arrived. In 2015, an excess appeared in the Large Hadron Collider data at a specific energy, suggesting the possible existence of a new particle. Physicists were cautious but excited. Theorists began working through the implications. Several hundred theoretical papers were published in the months following the initial result, exploring what kind of new physics might explain the anomaly if it were real. The excess disappeared completely in the next dataset, not reduced, not weakened, gone entirely. The particle did not exist. The 3 sigma excess had been a statistical fluctuation. All that theoretical work, all those papers, all that redirected attention was wasted on a fluctuation. This history makes the community very cautious about anything below the 5 sigma threshold. 5 standard deviations of significance means the probability of the result arising from random fluctuation is less than 1 in 3 million. The threshold is deliberately set at this demanding level because the cost of a false discovery, years of theoretical effort chasing a signal that turned out to be noise, is enormous. The current anomalies in kaon decay rates and B-Meson branching ratios sit in a range that particle physicists take seriously, study carefully, and build theoretical models around, but do not yet treat as confirmed. The most persuasive feature of the current situation is not the magnitude of any individual deviation, but the consistency across independent measurements. The same directional tilt appearing in 5 or 6 different measurements of different particles run by different teams using different instruments is substantially harder to dismiss than a single 3 sigma result in one measurement. Random fluctuations do not preferentially point in the same direction across multiple independent experiments. Systematic signals do. Theorists are divided on what to make of the current picture. Some argue the combined pattern is already compelling enough to build serious theoretical models around. Others hold that no individual measurement has yet individually crossed the bar, and the apparent pattern could still dissolve with more data. Both camps agree on what resolves the question definitively: more statistics, more collisions, more rare events. The high luminosity upgrade delivers exactly that. Physicists are already thinking past the question of whether the standard model breaks. They are thinking about what happens in physics when it does. The standard model has been stressed before and absorbed the challenge by extending itself. The discovery of neutrino oscillation required extending the model to include neutrino masses. Evidence for 3 generations of quarks required extending the model to accommodate more internal structure than originally expected. Each time new data demanded something new, the framework expanded to include it without requiring a wholesale replacement of the underlying language. The collection of open problems accumulating now feels qualitatively different to many researchers. The combination of unexplained dark matter representing 85% of all mass, the matter-antimatter asymmetry that current physics cannot account for, the neutrino mass problem with no satisfying natural mechanism, the Higgs stability question, and the rare decay deviations all pointing toward the same territory simultaneously suggests not a gap to be filled, but a sign that something structural is absent from the framework. Several serious theoretical proposals exist. Supersymmetry proposes that every known particle has a heavier partner related by a symmetry between matter and force, with these partner particles providing dark matter candidates, addressing the Higgs stability problem through the contributions of superpartner loops and generating additional charge parity violation. The collider has searched for supersymmetric particles across a wide range of masses and found nothing. The absence has ruled out the simplest and most naturally motivated versions of the theory, but has not ruled out the full theoretical landscape. Composite Higgs models propose that the Higgs boson is not a fundamental point particle, but is itself built from smaller constituents held together by a new undiscovered force, analogous to how protons are built from quarks bound by the strong force. This structure would naturally explain why the Higgs mass sits at its observed value rather than being driven to much higher values by quantum corrections, and it predicts new resonances at energies the high luminosity machine can probe. Extra spatial dimensions, proposed in several independent theoretical frameworks motivated by the hierarchy problem, would change how gravity and the other forces behave at very short distances and could explain why gravity is so extraordinarily weak compared to the other 3 fundamental forces. Some extra dimension models predict the appearance of towers of heavier partner particles for known particles at mass scales potentially accessible to the upgraded machine. None of these frameworks has been confirmed. Each makes specific, testable predictions that the upgraded machine will probe with unprecedented precision. Whatever the correct theory beyond the standard model turns out to be, it will have to pass the most demanding test in physics, explaining why the standard model works so extraordinarily well at every scale currently tested while breaking down at smaller scales. That is a very tight constraint. Most proposed extensions fail it by predicting effects that should already have shown up in existing data. The theory that passes this constraint, when it eventually arrives, will be one of the great intellectual achievements in human history. The universe has 4 known forces: gravity, which acts between every massive object in the universe, holds planets in their orbits, organizes matter into stars and galaxies, and on the very largest scales shapes the overall structure of the cosmos. Electromagnetism, which acts between electrically charged particles, drives every chemical reaction, carries light across the universe, generates the forces that prevent solid objects from passing through each other, and underlies every electrical and electronic technology ever built. The strong nuclear force, which acts between quarks and binds them inside protons and neutrons with an intensity that makes it the most powerful force in the known universe at short range, stronger than electromagnetism by a factor of approximately 100 at the distance scale of an atomic nucleus. The weak nuclear force, which is responsible for certain types of radioactive decay and for the nuclear reactions that converted hydrogen into helium in the first few minutes of the universe's existence, and that continue to power certain types of stars. These four forces, described mathematically by the Standard Model plus general relativity, account for every physical phenomenon ever directly observed by any human instrument. And yet physicists have strong reasons to think they are not the complete story. The theoretical problem that points most clearly towards something deeper is that gravity is wildly, inexplicably weaker than the other three forces. Pick up a small iron nail and hold it over a table. A small refrigerator magnet, brought close to the nail, will lift it off the surface, overcoming the gravitational pull of the entire mass of the Earth acting on a small piece of iron. The entire Earth versus a small magnet, and the magnet wins. Gravity organizes galaxies and governs the large-scale structure of the universe across billions of light years. But at the scale of individual particles, it is so faint compared to electromagnetism and the nuclear forces that it is essentially irrelevant to particle physics calculations. This enormous gap between gravity's strength and the strengths of the other forces is called the hierarchy problem. It suggests that either the fundamental equations of physics contain a fine-tuning of extraordinary precision that has no theoretical justification, or that additional physics exists at scales between the Standard Model and the Planck scale that connects the different force strengths and explains the apparent weakness of gravity in a natural way. Every major theoretical extension of the Standard Model was built at least partly to address this problem. Finding evidence of any of them in the upgraded machine's data would be the first step toward resolving it. Dark matter has to be something. This statement, simple as it sounds, is the foundation of one of the most extensive experimental searches in the history of science. The gravitational evidence for dark matter's existence is so overwhelming, coming from so many independent directions, that it is not seriously in doubt. What is in doubt is what dark matter actually is. The leading candidate for decades was a class of particles called weakly interacting massive particles, known in the physics community by the acronym WIMPs. The theoretical appeal of WIMPs was strong to the point of being almost suspiciously convenient. If you extended the Standard Model through supersymmetry, you automatically got a new heavy particle that interacted only through the weak force and gravity, that was stable on cosmological timescales, that would have been produced in the right quantities in the hot early universe, and that would be present today in quantities matching the observed dark matter density. This combination of properties arising naturally from a theoretically motivated extension of the Standard Model made WIMPs the dominant dark matter candidate for decades. Experiments went looking with great sophistication. Underground detectors filled with liquid xenon, cooled to near absolute zero and shielded from background radiation by hundreds of meters of rock, waited year after year for the rare occasion when a dark matter particle interacted with an atomic nucleus. Nothing. Progressively larger, more sensitive detectors were built and operated for longer periods. Still nothing. The collider searched for missing energy and momentum signatures indicating WIMP pairs created in collisions and escaping the detector invisibly. Nothing across 2 full run periods covering a wide range of energies. The absence of WIMPs in detector after detector, including the Large Hadron Collider, across multiple search strategies, has pushed the field to take seriously alternatives previously considered less elegant or less theoretically motivated. Axions are one compelling alternative, originally proposed not to explain dark matter, but to solve a different problem in the theory of the strong nuclear force. Axions would be extraordinarily light particles that convert into photons in the presence of a strong magnetic field, producing detectable light in experiments specifically designed to exploit this conversion. Multiple experiments worldwide are currently hunting for this signature at different mass scales and coupling strengths. Some have recently achieved the greatest sensitivity ever reached. The search continues. Primordial black holes, formed in the extreme density fluctuations of the very early universe before any stars existed, represent another alternative that requires no new particle physics at all, only the application of known gravitational physics to early universe conditions. Observations of gravitational microlensing events and gravitational wave detections are being used to constrain how much of the dark matter budget could be accounted for by objects in this category. None of these candidates is confirmed. The high luminosity upgrade will probe the remaining parameter space where WIMPs could still be hiding with unprecedented depth. If a definitive non-detection emerges after years of running at 10 times the current collision rate, covering the full theoretically motivated mass range, it would rank as one of the most important negative results in physics history, effectively eliminating the dominant dark matter candidate and forcing a complete reconsideration of what the invisible majority of the universe is made of. There is a number sitting in the equations of cosmology that has no explanation anywhere in physics. Physicists call it the cosmological constant. Einstein introduced it as a term in his field equations for general relativity in 1917, added to prevent the mathematical solutions from predicting a universe that either collapsed or expanded, because at the time the dominant assumption was that the universe was static and eternal. When observations in the late 1920s confirmed that the universe was expanding, Einstein reportedly described the cosmological constant as his greatest mistake. He removed it from his equations and moved on. Then in 1998, 2 independent teams of astronomers studying the brightness and redshift of distant Type 1a supernovae, exploding stars used as standard candles to measure cosmic distances, discovered something that overturned the dominant expectation entirely. The universe was not just expanding, the expansion was accelerating. The galaxies were not just flying apart, they were flying apart faster and faster with each passing billion years. Something was acting throughout all of space, driving it to expand with increasing speed. The cosmological constant returned, not as Einstein's error, but as the mathematical description of something physically real. Physicists now call it dark energy. The problem is not that dark energy exists. The problem is the number. Quantum field theory, the framework that underlies the entire Standard Model, predicts a value for the energy density of empty space based on the quantum fluctuations of all the fields that permeate the vacuum. When physicists calculate this theoretically predicted value and compare it to the observed value of the cosmological constant derived from the supernova measurements and the cosmic microwave background, the two numbers disagree by a factor of 10 to the power of 120. That is 1 followed by 120 zeros. The predicted value and the observed value differ by a factor that is larger than the total number of atoms in the observable universe. This is not a rounding error. This is not a matter of getting a coefficient slightly wrong. This is the most catastrophic quantitative failure in the history of theoretical physics. A prediction that is wrong by a margin so vast it is almost impossible to express in ordinary terms. Something is cancelling the enormous predicted vacuum energy down to the tiny observed value with a precision of 120 decimal places. No mechanism in the standard model performs this cancellation. No extension of the standard model that has been proposed and tested provides a satisfying explanation for it. This failure has been understood and discussed in the physics community for decades. Physicists call it the cosmological constant problem. It remains completely and entirely unsolved. The collider cannot directly measure the cosmological constant. But the new physics it is hunting for, whatever explains the kaon anomalies, or dark matter, or the Higgs stability, might connect to the mechanism that controls the vacuum energy. Theories that address the Higgs hierarchy problem frequently have implications for the cosmological constant problem. The two problems may not be separate issues requiring separate solutions. They may be two symptoms of the same missing structure, the same absent piece of the theoretical puzzle that, when eventually found, will account for both simultaneously. The physics community's growing willingness to discuss both problems in the same breath reflects a shift in perspective. The collection of open questions has grown large enough and coherent enough in the direction it points that a single deeper explanation connecting them all is beginning to look more likely than a series of independent patches applied to the existing framework. Physics discoveries do not arrive with drama. The Higgs boson discovery in 2012 was announced in a crowded auditorium with a slideshow. The result was a set of data points plotted on a graph. A bump in a histogram of collision rates at a specific energy rising above the background noise with enough statistical significance to cross the 5 sigma threshold. That bump was the particle. The celebration in the room was genuine and deserved. The graph itself looked unremarkable to anyone not trained in reading particle physics plots. A future discovery of new physics beyond the standard model will look similar. A deviation in a kaon, decay measurement, climbing from 2 sigma to 3 sigma to 4 sigma to 5 sigma as the data accumulates over years of running at high luminosity. Or a new resonance, a new bump in an energy histogram, appearing at a mass that no known particle occupies. Or a systematic missing energy signal that grows more significant with each additional run period and cannot be explained by any known process. The process leading to a discovery claim is slow, deliberate, and layered with verification steps. When a potential signal appears, the team that found it does not immediately announce it to the world. Internal reviews begin immediately. Independent subteams within the same experiment reanalyze the data using different statistical methods, different background models, different systematic uncertainty estimates. Every known source of background or instrumental artifact is scrutinized. The potential signal is stress-tested from every angle to make sure it is not a product of how the data was collected, processed, or analyzed. If the signal survives internal review, a paper is submitted for external peer review, and other experiments running complementary analyses are quietly asked to check their own data for the same signal, only after independent confirmation from a second experiment or after the original experiment accumulates enough data to push the significance convincingly past 5 sigma does the result cross the threshold into accepted discovery. This process is slow. It is sometimes agonizingly slow for the physicists closest to the data, and it is exactly why the discoveries that do clear the bar carry the weight they carry and last as long as they last. A confirmed discovery of new physics at the High Luminosity Collider would cascade through the entire scientific world in ways that are genuinely difficult to overstate. Every open question currently sitting at the edge of the standard model would suddenly have an empirical anchor. Every theoretical framework that makes predictions in the discovered territory would immediately be tested against the new measurement. The questions physics has been building toward for half a century would finally have something real to organize themselves around. And the universe, which has been hiding its deepest rules for 13.8 billion years, while we have been asking questions for a few centuries, would finally be giving us one more piece of the answer. The machine buried under Europe is one step in a search that will outlast everyone working on it today. The conversation with the universe is just beginning to get interesting.